Okay, chapter 8 is where we took a little bit of a turn and we started looking at rectangular and polar. We did a lot of complex number stuff and then also finished up with vectors. Here's the 5 big topics that we did. Not that I'm going to give you 5 questions because some of these topics can be rolled in together, but basically this is what you're responsible for out of this chapter. First thing is how we go from polar to rectangular and also rectangular back to polar. We've had this picture here and we came up with these equations. So you may want to add that to your note card. A quick little example. You want to find the rectangular coordinates for the following polar. We know they're in polar because polars are always radius comma thetas. So let's take, we'll do B here. Using the equations we came up with from our picture, we see all we have to do is plug in an r and plug in a theta for each x and y, and now we just need to evaluate this. So once it's set up, all we got to do is go plug things in. So we draw a triangle at 5 pi over 4. Cosine and sine are the same things at 45s. Taking care of the sines, both these come out positive. 2 square roots of 2, 2 square roots of 2, there's your x and your y. The reason that works is if you were to plot this, 5 pi over 4 takes you here, the negative radius bounces you back to quadrant 1, so both things can be positive. If we want to go the other way, so find polar coordinates, so here's a rectangular one, draw a picture, set up everything you can. So we know we're in quadrant 2. We need to figure out that theta. Just a simple Pythagorean theorem will give us the radius. You can do whatever trig function you want. If you choose to do a tangent like I did here, it's going to spit out a negative 53 at you. And that goes back to inverses. Inverse tangents are only defined in 1 and 4. So that'll tell us the reference angle there. So we just need to do subtract the value from 180 and we'll get 126 degrees. We know anything in polar is an r comma theta. If you do it in degrees, it's not wrong. You're usually going to see answers in radians here. So you can see on the calculator how we adjusted to get those. So you'll get decimals because they are radians, then you can add pi to it. Here's the one piece of De Moivre's theorem we're actually going to do instead of that big complicated one finding all the complex roots. We want to expand these. So we said a complex number in polar form has cosines and sines. So you need the I to show that it's a polar. If we want to expand it, we could sit there, we could double distribute this 4 times. Again, that's really, really ugly. So De Moivre came up with this nice, neat theorem for us. Only problem is we need a radius and we need a theta based off this right here. So if we draw a picture and put in what we can to represent this point up here, we'll see that the reference angle is 30. We're in quadrant 2, so that means we have a theta of 5 pi over 6, and then we can just grab the radius of 2. So you can go radians, you can go degrees. Degrees are probably easier in this case. We go ahead and we plug it in just according to the formula, and we get here. Now we look at what they want. They want it in an a plus bi, so we need to take this and simplify it. If you simplify 600, you get the same thing as 240. Draw a picture or use your unit circle. Both sine and cosine are negative. Plug in the values. Don't forget about the I. Distribute the 16, and this is what we get. Okay, moving on to the vectors. Magnitude, real quick again. If I give you any vector, the symbol is 2 parallel lines up and down on each side. So if I want the magnitude of vector v, it's just kind of like a Pythagorean theorem or a distance formula almost. A squared plus the b squared. There shouldn't be any negatives in there because negative numbers are always squared, and we just take the square root of it. Dot product. I give you any 2 vectors, whether they're 2D or 3D vectors. Dot product is you multiply the I components, you multiply the J components, you multiply the K components if they're there. Dot product always gives you a number. Here's where you would use those. Angle between 2 vectors. So if you get 2 vectors in space or on a plane, this formula, we actually use a law of cosines to come up with this. This formula will tell you how to do it. So cosine of what the angle you're looking for, you dot the two vectors on the top, you do magnitude of the two vectors on the bottom, and then you just inverse cosine that and get a number. You can see the work over here between a vector u and v, dot on the top, magnitude on the bottom. So we go ahead and we plug everything into the formula. We're just going to do an inverse cosine here. So 63 degrees is the angle between these vectors. We don't have to worry about adjusting formulas or anything because inverse cosines are in 1 and 2, which takes us up to 180, which is all that can be an angle between vectors. Cross product. This is where we use the discriminants in the little matrices here. So we do this for three-dimensional vectors. They all have an A, B, and a C component, or I, J, and K. Here's the setup for it. So what we did to get the I values, you cross off everything in the I going sideways and down, and you're left with this little square here. To find the values of these, you do discriminants. So you cross multiply, and you're always subtracting in between. You move on to get the J components. So you cross out J down and across, and you're left with this here. Okay, again, you would do the discriminant between those with subtracting. And lastly, to get the K components, you would do the same thing and cross those out. Now the formula does go minus and plus, so make sure you have that written down as well. Everything in between is minus signs there. You will get a vector out of this. So something I minus something J plus something K. By definition, cross products are perpendicular, which is another word for orthogonal to two vectors. So if you have a vector in space here, you have another vector in space here, and you found the cross product of those, by definition, the cross product would be perpendicular to these, orthogonal, so basically coming out the screen at you. Okay, so U cross V is orthogonal to U and V. So I may not say find the cross product of two vectors. I may give you two vectors and say find the vector orthogonal to them, so you should know by definition that is a cross product. Okay, chapter 8, we made it in under 8 minutes with about 20 seconds to spare. So bring any questions you guys still have to